Alright, hey everyone, so this is chapter 10. We're doing acids and bases today. Uh, it shouldn't be too long, so I've also included some videos on Cougar View under content, um, links to different YouTube videos. I went through and watched a bunch of them. I think these are the most helpful, so I've kind of labeled them in what they help you do for this section, but you want to watch all this lecture uh, because they use some words that you might have not heard yet, so you might need to have this as kind of a reference to draw on when you watch some of those. But anyway, let's see. I have to post this PowerPoint. I'm going to kind of follow through it. Sometimes I'll use the text, sometimes I'll use the PowerPoint. It's chapter 10 in your text: acids, bases, and equilibrium. Okay? And so there's several definitions for acids. There's the Bronsted-Lowry definition and the Arrhenius definition. We'll discuss both. But like I said, I'm going to kind of use this PowerPoint and go through there. I'll stop when I need to, and give me just a second. Stop when I need to so I can show y'all some things on the iPad or whatever. Okay, so an acid, according to the Arrhenius definition, so we'll talk about the Arrhenius and Bronsted-Lowry. Typically, the Bronsted-Lowry is the one that we're using and referring to, but it's important to know both for this course, okay? So the Arrhenius acid is something that produces a hydrogen ion when they dissolve in water, okay? And so counter to that, the Arrhenius base is something that produces a hydroxide ion in water, okay? So that's the way I typically think about it. You have hydrogen ions. Oh, sorry, I want to go to my iPad. Yeah, I might not need to do that presentation mode because it's too hard to get in and out of it. Okay, so an acid, the Arrhenius definition is something that produces a hydrogen proton. I like to call it a proton because if you remember, hydrogen has one proton, one electron. Well, since it has this plus charge, I've lost the electron. So essentially all I have here is a proton because its mass is 1, so it also doesn't have a neutron. Um, so anyway, an acid produces a hydrogen proton, and then a base produces what we call a hydroxide anion. Okay, so you'll see this as hydroxide. Um, and this can either be called a proton or a hydrogen ion. Um, there might be something else that's called. I won't say it unless it's brought up later. Okay, so, and then another way I like to think about it is the charges, okay? If it's an acid, it's going to have an abundance of plus charge, okay? That's a circle, okay. And then if it's an acid, it's going to have an abundance of minus charge. Okay, so just kind of keep that in mind, and that's true for everything. The Bronsted-Lowry, the Arrhenius, any definition of acid is going to have something to do with a positive charged ion, and then anything to do with the base is going to have something to do with a negatively charged ion. You'll see, for the most part, you'll see what I mean. All right, so let's go back to the slideshow display. So an Arrhenius acid is something that produces a proton or a hydrogen ion. Um, so a couple notes. It also is an electrolyte because we said an electrolyte is anything that has the ions in there and can transmit electrons. Um, Some other key properties of acid is it has a sour taste, it turns blue litmus paper red, and it can corrode metals. Okay, so these little, the sour taste is especially gives it away. Most acidic drinks are a little bit sour. We'll talk about bases are kind of chalky and smoother to texture and taste wise. Okay, so when we talk about naming acids, I included a good video on this, but just kind of a short go-to. If it doesn't have an oxygen, then we use the prefix hydro. And so you're familiar with a lot of these: hydrochloric acid, hydrobromic acid, hydroiodic, and hydrocyanic acid. Cyanic acid actually breaks down to make cyanide, so you've heard of that as well. Um, if it has an oxygen, so you use the hydro. If it doesn't have an oxygen, then you just add the IC acid on the end. If it doesn't have an oxygen in it, then you're going to change the last bit, whether it's say sulfate to sulfuric, okay, or sulfite to sulfurous. And so you'll notice a little trend here. This chart might actually be good. There's a better one in your text. It'll pop up here in a few slides, but drop anything that is ATE, drop it and replace it with ic acid. So sulfate becomes sulfuric acid, nitrate becomes nitric acid, acetate becomes acetic acid. All right. So anything that ends in ITE, nitrite, sulfite, phosphite, drop the ITE and end in OUS acid. So nitrous acid, nitrite becomes nitrous acid, sulfite becomes sulfurous acid, and phosphite becomes phosphorus acid. Okay? So it's really simple, but there's a chart that you can print up here in just a minute when we get to it that kind of ranks them as how strong they are. That's the one that I'd keep because you get the names from it and you also get the strength, the relative strength of the acid or base. Okay, so when I get there, I'll highlight that and say this is something you need to hold on to, maybe print out for the exam. Okay, so let's go through these. So select the correct name for each of the following acids. Remember, if it doesn't have an oxygen, it's hydro. So I know that that's C, right? This one is a carbonate, right? So if it's an 8, it's got to be IC acid, right? Because ite turns into OUS, 8 turns into IC. And this has oxygen, so it's not hydro, it's got to be A, right? Carbonic acid. This one has an oxygen, so no hydro, can't be B. Is that bromate or bromite? I think it's bromate, so that would also be A, but I'm not sure. This is when you need your chart. Bromate, bromite. That has to do, the ite and the 8 has to do with the charge. So like I said, it's good to have your little list there. I don't ever see that one, so wasn't familiar with it. Let's see. Arrhenius bases produces hydroxide ion. So we said that earlier. Look for that little minus, the OH minus. Tastes bitter, chalky, slippery. I said kind of smooth. They describe it as soapy or slippery. Like if you get, what's a good example? Like a Malox or what's the stuff, the pink stuff? Pepto-Bismol. That's kind of like a basic solution that you drink and it kind of neutralizes the stomach acids that are acid reflux or indigestion, heartburn. Um, it's kind of smooth and chalky, almost like a milky kind of taste. That's what a base or basic solution is going to kind of taste and feel like. All right. turns litmus paper blue. And then we also use what's called an indicator, phenolphthalein, which you'll see that in your labs when we do our labs. So we'll talk about that more. But when a solution becomes basic and it has phenolphthalein in it, it'll turn pink. Okay? All right. So here's some common bases. You'll notice that you just, whatever the first element is, you name that element and then just say hydroxide. You don't have to tell me how many hydroxides, dihydroxide, trihydroxide. You balance it based on the charge. We said hydroxide has a 1 minus charge. So when I balance it with sodium, which has a 1 plus charge, I only need 1 hydroxide. Barium, on the other hand, or calcium, has a 2 plus charge. Therefore, I need 2 hydroxides to balance that molecule. And so that's all you're seeing here. Aluminum has a 3 plus charge, so I need 3 hydroxides to balance that molecule. And that's how you know how many hydroxides are behind it. Okay, so let's match the names. This is a nitric acid, nitrous acid. Okay, it's got to be D. Calcium hydroxide, E. Sulfuric acid. Remember, if it's got the oxygen, it's not hydro. And then the SO4 is a sulfate. I know that is a sulfate, so I drop the ATE, turn it into IC, and that's sulfuric acid. Iodate, I think that's iodate. So that would be iodic acid. And then sodium hydroxide. Now, the Bronsted-Lowry theory, I can't say that, Lowry. So an acid is a substance that donates an H plus proton, okay, so a hydrogen ion. And then a base is any substance that accepts the hydrogen ion. Okay, so this is going to create a system. Let me go back to my iPad. All right, so this creates, I'll be able to go back and forth. Yeah. A situation where everything in your equation is essentially an acid or a base, okay? And let me explain what I mean by that. So let's say I'm mixing hydrochloric acid with water. No, don't do that. Okay, hydrochloric acid with water, right? Okay, so this is going to be the hydrogen proton that I'm giving up to the water, right? So according to Bronsted-Lowry, this will be my acid, and this will be my base. Okay, so now let me draw the other side of the equation. On this side, I am going to have a chlorine that's by itself with a negative charge. And I'm also going to have a water that has picked up 1 extra hydrogen proton, and it's now a positive charge, okay? So this is why I was talking about the charges. Remember, if it's got a positive charge, think acid. If it's got a negative charge, think base, okay? So, according to Bronsted-Lowry, and we'll go back to this, an acid is a substance that donates the H. A base is a substance that accepts the H. So here's that equation that I just drew on my iPad. HCl plus water yields H3O plus chloride ion Cl minus. Okay, so the acid is the HCl, right, because it's giving up that H. The base is the water because it's the one accepting it. And now they create what we call conjugate pairs, okay? So the conjugate pair, the acid always makes a conjugate base, and that would be this chloride here. And then the base always makes a conjugate acid, which would be this, what we call a hydronium. Let me write that on here. An hydronium ion, okay? H3O is hydronium ion. and it's always got a little plus charge. So we call this the conjugate base, and I'm just going to abbreviate it as CB. Okay, and then this hydronium is the conjugate acid. All right, so just remember, if it's got that negative charge, it's got to be the conjugate base. If it's got the positive charge, it's got to be the conjugate acid. All right, so let's look at a little bit more of that. Where am I at? Right here. Okay, so here we're doing ammonium and water. So the ammonium is actually the thing accepting the hydrogen in this case. So it's the base. The water is what's giving up that hydrogen proton, so it'll be the acid. Now do your conjugate base pairing, right? So the NH4 plus would be the conjugate acid because I have that plus charge. The hydroxide would be the conjugate base because I have that minus charge. Okay? So it's pretty easy to kind of keep straight. Whatever's accepting the hydrogen is the base. Whatever's giving it away is the acid. And I usually remember that because of like hydrochloric acid, hydrobromic acid, hydroiodic acid. They can only give the H away. So they're always the acid, right? And then I'll start from there and then kind of figure out what I'm talking about here. Because you can see instances where the H can be given away or taken. Okay, we'll talk about that in a little bit. There's buffers and other things like that where they can do both. So this is just a little chart that kind of lines out the different properties and characteristics between acids and bases. Okay. In each of the following equations, identify the Bronsted-Lowry acid-base in the reactions. Oh, this automatically, that's why I want to do present. Let me go back to present. Okay, so the HNO3 is what's giving up the hydrogen. That'll be the acid. That makes water the base, right? The plus sign on the hydronium, so that's the conjugate acid. The NO3 has the minus, that's the conjugate base. Hydrofluoric is obviously the acid because it can't do anything else. It has to give up that H. The water is the base in this case, and then the hydronium, once again, the conjugate acid. The fluoride ion is the conjugate base. And like I said, I'm just looking for the charges that kind of automatically tells me conjugate acid, conjugate base. Sour taste acid produces hydroxide. That's got to be a base. Chalky taste, base. Electrolyte, both are electrolytes because both are ionic, right? Anything with a positive or a negative charge is an electrolyte. So, and it dissolves in a solution. So, both an acid and a base are both electrolytes. Produces hydrogen ions in aqueous solutions. That's an acid. And this kind of goes back through the conjugate acid-base pairing. But I think, the positive, negative, that's the best way to kind of keep up with it. Conjugate base for each of the following. So remember, the conjugate base is whatever the negatively charged part left over is. Okay, so in A, it'll be the bromide ion. In this one, it'll be 1H short, right? Because you only take away 1H at a time. So now it becomes HS negative. All right. Same goes for this carbonate here. I can only take away 1H when I make a conjugate base. So now it'll be HCO3 negative. NO2, so it has a negative charge. If I add a proton, it'll be HNO2. NH3 is neutral, so if I add a proton, it's going to be positively charged, right? It's going to become NH4 positive. You got to remember when you're moving the hydrogen proton around, it's taking a plus charge with it, okay? OH adds a H plus and it actually becomes water. So acids and bases neutralize each other. If you combine a hydrogen proton, an H plus an OH minus, that'll yield water. Let me go to my iPad. I want to show you all that on paper just so you can kind of see. And do it again. Come on. There we go. All right. So I said that a hydrogen proton plus a hydroxide will yield water. Okay, so this is called a neutralization reaction. And this is essentially the fundamentals of acid-base chemistry. Okay, a hydrogen proton plus a hydroxide ion equals water. Okay, and so neutral water has the same amount, or I say neutral, pH 7 water has the same amount of H as it does OH, because, and they balance each other out. Okay, if it's more acidic, it'll have more of this. If it's more basic, it'll have more of this. The hydroxide. That should be circling, sorry. I gotta move it right over my router. But anyway, you get the gist. So the other point I wanted to make about this froze up again. The other point I wanted to make was that I can only take away one H, right? I said that when I take away an H from the, what is this, hydrogen sulfide, well, let's do plus water, yields, there it goes, HS minus plus H3O plus. Circle those charges. Okay, so notice that you can only take away one of the H's, but when I do, this was neutral right here, right? There's nothing there. So when I take away one of the H's, it becomes negatively charged. All right, I don't want y'all to lose sight of that. Keep up with your charges. If I take a proton away, it's going to get negative. If I add a proton, which is what I'm doing to water, it goes from neutral, right? There's nothing here. That's supposed to be a blank, not a minus. To positively charged when I add a proton. So keep up with that proton as it moves. It's going to change the charges, right? The other problem they did was H2CO3. Let's say I add that to water. Yields HCO3 negative plus H3O positive. Okay? And so notice that my charges are still balanced, right? The minus charge from this plus the plus charge from that is still neutral. So that's how come this system in this equation is still balanced, all right? Just make sure you keep up with the proton. When you're moving it around, you're going to change the charges a little bit. It's important to keep up with that. I noticed on some of the lab reports that you were kind of leaving the charges off or even putting them maybe not where you should have, right? So just kind of keep up with that. All right. Back to present. Oh my gosh. I'm not very computer savvy. I don't know if y'all noticed that over this semester. We're almost done. You know, I think, is this the last chapter? Yeah, I think this might be the last chapter. My goodness. Okay, so when we get into reviews and stuff, I've actually got some good problems I want to work through. I'll do another practice exam and everything. Um, okay, so this is more conjugate acid base pairing stuff. I think you ought to be good on that. So I'm going to kind of roll through this. So the strength of acids and bases, this is important. Now I said to print this chart. This is the chart, right? And you'll find this on the internet as well. The relative strengths of acids and bases. You can kind of type that into your Google and you ought to get some kind of chart like this, kind of print it or write it down on a card and kind of save it on the side. So what this chart's showing you is how strong an acid each one of these compounds are. Okay, so you'll see the strongest acid is hydroiodic acid, then followed by hydrobromic acid, and there's only about seven strong acids. Everything else is a weak acid. Okay, so let's talk about what the difference between a strong acid and a weak acid is. Okay, a strong acid is something that completely dissociates. Let me back up to right here. Okay, so remember when we talked about electrolytes and ions in general, we said that when I put, like, say, salt into water, oh, you are still on display. Let me take you off of that. Okay, so remember when we put salt in water, we said that the salt will just keep breaking up, right, until the water completely surrounds all of the Na and all of the chlorine, the chloride ions. Um, so acids work the same way. A strong acid will work just like that. As soon as I put hydrochloric acid into water, it all splits apart and it becomes H plus and Cl minus. It all splits apart. Then the H plus will start to hook up with water and make that hydronium that we were talking about. Um, a weak acid doesn't all separate. Okay, some of the molecules stay together. And let me see if I can't find a example here. Okay, so this chart, these little charts on the left side of the PowerPoints is trying to indicate what I'm talking about. So when I put hydroiodic acid into water, all of the hydroiodic acid, you see how these charts, these bars are the same height? That means that I had the same concentration of H3O plus or the H plus and the same concentration of the iodide ion. That means all of the HA has broken to two. And so now I have the same number of H pluses and the same number of I's as I did of HI together, right? It was one piece and then I broke it apart. Now I have two pieces, but it's the same amount of each. So that's why that bar shows they're the same height. On a weak acid though, this is that same chart. Notice here that the purple is HF together as one molecule. Now on the right, you'll see the hydronium or the H plus is very low compared to that HF, and the fluoride ion is very low compared to that HF. Just to kind of juxtapose that with the acid, the strong acid. The heights of the H3O plus and the iodide were the same as the HI, the hydroiodic acid together. Then on the weak acid, it goes down significantly. Only a little bit of that HF is breaking apart. So just kind of, I'm going to do an illustration best I can. This is kind of how I imagine it. I imagine it as HF and HI is like one molecule. Imagine this is molecules floating around in the water, okay? And so I'll draw some waters out here, H2O, 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 right? So what happens with a strong acid is this splits apart always and forever, and it'll become H plus and I minus, okay? Now the HF, it may split apart, but more than likely it's going to stay together as HF. Okay? So this is the weak acid that only breaks apart sometimes, and then the strong acid always breaks down. Okay? And you can see how that would increase the concentration of H plus in the water, right? The strength of the acid is dependent on how much of these are in the water, so, or in the solution, whatever. It only makes sense that the more of these break down, the stronger the acid is. Okay? So that's kind of how I think about the strength of the acid and what a weak acid or a weak base means, right? It's weakly dissociating. We call it, when it breaks apart like that, dissociating. So it doesn't dissociate easily, is a better way of saying it, I guess. Okay. So just kind of something to keep in mind. Weak acids have a strong conjugate base. A strong acid has a weak conjugate base. And they just kind of work vice versa like that. And that also is makes sense because a stronger acid means that the H is breaking apart more easily. I think we just went through all of that to kind of say that. Well, if it's breaking apart more easily, that means that base is not very strong, because a strong base will hold on to that hydrogen proton very strongly, right? It'll almost just snatch it right up out of the water. So that makes sense in that regard. But I wouldn't think about it too much. Just kind of think it's the opposite. Weak acid, strong conjugate base. A strong acid, weak conjugate base. Strong base, weak conjugate acid. So on. Okay, just reiterating that point, right? HCl dissociates completely, makes 100% H plus and chloride ions. Acetic acid doesn't all break down. Most of it is still HC2, H3O2, and then a few of it actually breaks apart the H and becomes H plus and C2H3O2 minus. Okay. I feel like I'm kind of getting bogged down, so we'll skip on through that. Strong bases, just remember groups 1 and 2 when hooked up with a hydroxide. That's a strong base. Okay, there's a few other ones, but not a lot that you'll see. And this is a study check. You can kind of go through there. Just use your chart, right? Use your chart to compare the acids or the bases. There may be questions on Mastering Chemistry that compares the conjugate acid or the conjugate base. That's why I said it's important to remember weak acid, strong conjugate base, strong acids, weak conjugate base. And the same thing goes with bases. Strong base, weak conjugate acid, weak base, strong conjugate acid. All right, so now we're going to talk about equilibrium. Equilibrium is essentially just a balancing act. They got a good illustration here. Where's it at? I like to think about it like 2 tanks of water. Here it is. It's called Le Chatelier's principle. I can't speak this evening. I need some more coffee. So this is essentially like 2 buckets of water that are connected on the bottom. Okay, you see that? So all of these equations go through this little balancing act. All right, and I like to think about it like we're balancing water. Let me make sure y'all can see me. I still want to highlight this picture. Yeah, so on the left side, I'm looking at tank A to tank B, the water at equilibrium. So at equilibrium, it's balanced, right? The levels are the same on both sides. Now you got to imagine if these are connected and I pour some water into one side, it's going to push the water level down and push through the little tunnel and then raise the water level on the other side, essentially until they're balanced, right? If all things being equal, right? I can manipulate the situation where it holds it, but all things being equal, it's going to push that water level down until it kind of balances out. Also, you can think about like somebody smoking in a room, right? I got two rooms, they're closed off from the rest of the world, but I have an open door right in the middle, and air gets to pass back and forth. So if I have somebody smoking in one room and somebody not smoking in another, if they sit there and those rooms are connected and that door is open for long enough, eventually both rooms are going to smell like smoke. Okay, so that's kind of this balance that I'm talking about. Uh, in the case of this water, these tanks that we're looking at, and Le Chatelier's principle, if I pour water on the left side, which thinking about a chemical reaction would be the reactant side of the equation, correct? If I pour water into this left side, then it's going to push the balance to the right. It's going to make the right increase. Okay? So that kind of happens. Let's think about it conversely. Say I take water out of the left side, right? Now the right side's more heavy, right? I got more water in this right side. It's going to push back and raise the level of the left side. So all these chemical equations do this same thing where they try to reach what we call equilibrium, a balancing act, right? Where it kind of pushes back and forth until it gets stable. We call it stable, or equilibrium is reached. I want to back up. Let me go back into presentation mode real quick. Weak, weak, strong. Okay. Yeah, so equilibrium is essentially saying that it's going the same speed forward as it is backwards. Remember, reactions most of the time can go back and forth, right? This is looking at hydrofluoric acid mixing with water. Remember we said hydrofluoric is a weak acid, so it doesn't dissociate that much. Well, this fluoride ion will break away, but then it'll join back up. Okay, it'll float around and it'll run into another hydrogen proton and it'll join back up, pull it off of the water, and then we're back to the left side. Okay, so all of Chatelier's principle in equilibrium is saying that there is a steady rate between the forward and backward reaction. Okay? So before equilibrium is reached, the concentrations of reactants and products are not the same. They have to change. Initially, reactants have a rate of reaction faster than the rate of the reverse reaction. When I first start the reaction, it's all going forward. It doesn't reach equilibrium until later when it starts kind of pushing back, right? And so you can think about the water the same way. Like just imagine I have to fill up that whole tub from the left side, and so I'll fill it all in, pour the water, it'll push to the right side, and then eventually maybe it'll push too far at first, and then it'll kind of balance back out. That's how equilibrium essentially works. At equilibrium, the rate of the forward reaction is equal to the rate of the reverse reaction, and at equilibrium, the concentrations of the reactants and the products are the same, stay the same, do not change. Okay. All right, and I'm gonna have some more practice on this on mastering chemistry. I don't think I did anything with the videos, with the YouTube videos on that, just because most of what I did there was focused on the math portion. The seesaw illustration is also a good way of thinking about it. It changes the balance of the equation, right? If I add to the reactant side, it's going to make the product side go up. Yeah, if I take away reactant, it's going to drop down. The reactant side is going to drop down. And that's essentially saying the rate, right? All of the, for the seesaw is for the rate of change. All right, I do want to do some math before I let y'all go. Dissociation of water. Okay, there's also a good video on this, but I kind of want to touch on it and maybe do a couple examples. I might show you on my calculator. Let me clear this and get this ready. Okay, so water is amphoteric, and what that means is it can act as an acid or a base. Remember I said that earlier, that some things can accept the hydrogen proton, but they can also give it away. And so water is a good example of that. In fact, if you are thinking about just a regular glass of water that you pour out of your kitchen, it always has some acid and some base in there, okay? It's not just a stable molecule. It always stays H2O. It's H3O plus sometimes it's OH minus, and they're constantly throwing these protons back and forth at each other, okay? And then how much acid or how much hydrogen plus stays in the water, that's how acidic it is. So amphoteric just means that it can be an acid or a base, and water is amphoteric. There's a few others, but we're talking about water because the concentration of hydrogen. Okay, so a pH scale, and I also put this on one of the YouTube videos. The pH scale is based on the concentration of hydronium ions. Okay, this H3O plus right here. All right, and it's actually the negative log. Let me find that slide just so I'm not talking about something that's not here. Well, hold on. I don't know why they don't talk about the log first, the pH scale first. Okay. No matter. All right. I'll back up and I'll start over. Don't worry about pH till I get there, I guess. So the KW, water has what is called an ion product constant, or KW. I'm going to write this on here. And it is always equal to 1 times 10 to the negative 14. Okay? And I said that neutral water has the same amount of hydroxide. Let me make sure you are seeing me and not the display. Okay, has the same number of hydroxide as hydronium. So I'm looking right here at H3O plus equals OH minus. That means they have the same number of H3O as I do OH minus. So let me pull up my iPad. If KW is equal to 1 times 10 to the negative 14 and H3O times concentration of OH minus equals KW. I wrote that too big. Concentration of H3O. These little brackets just mean concentration, if you hadn't seen that yet. And then times the concentration of OH minus equals KW. Okay? So this is the mathematical basis for everything that you're going to do concerning concentration. Remember, these brackets means concentration. Concentration of hydronium ions, or concentration of protons, hydrogen ions. H3O plus can also be thought of as H plus concentration. Okay, but I'm going to take that off because I don't want it on there right now. All right, so we said KW is equal to 1 times 10 to the negative 14. And remember, KW is called the ion product constant. All right, KW for water. The W stands for water. All right, so if that equals 1 times 10 to the negative 14, then that means both of these have to be because these are the same, 10 to the negative 7, and 1 times 10 to the negative 7. Okay? So that is the concentration of hydronium and of hydroxide. And I can write it like this too, right? Because we talked about molarity. So that's the concentration of hydroxide and of hydronium. Now, if I know all of this information, I can calculate any concentration that I'm given in, say, a problem or something. So let's look at one and let's just try to do it. These are all just kind of reiterating that fact. Pure water is neutral. pH 7, that's why I said I don't know why they didn't bring up pH first, but when the pH is 7 and the water is neutral, I have the same concentration of H3O plus as I do of OH minus. If I get a little more H plus, it becomes acidic. If I get a little more OH minus, it becomes basic. Now I'm looking for, and that's all these slides are saying. That one sentence I just said covered them 4 slides. Let's see. No, there's a practice problem here. Okay, what is the hydronium concentration of a solution if the OH minus is 5 times 10 to the negative 8? Okay, so I'm going to leave y'all there and I'm going to write this information down. OH minus equals 5 times 10 to the negative 8. Correct? Is that right? Yeah, okay. So here is my problem, right? And I said that Kw equals H3O times OH minus. Now I took that time sign out. You see here I have a time sign, but here I don't. You don't. Come on. Just a second. It'll catch up. Okay, so yeah, back up here up top. This one has a multiplication sign and the one below it does not. So you can do it either way. I would prefer that you do it without the multiplication sign because I know that the brackets means it's a concentration, and a bracket beside a bracket like this means I'm multiplying them with each other. Okay? So if I know Kw equals H3O times OH minus, then I can divide Kw by OH minus to get H3O. And that's what we're going to do. So I said the OH minus was 5 times 10 to the negative 8. I know Kw is always 1 times 10 to the negative 14. So let's do that. 1 times 10 to the negative 14 divided by 5 times 10 to the negative 8. All right, let me pull y'all to my little calculator here. 1 times 10 negative 14. Should put that in brackets. No, not that one. Bracket and bracket. Now all of that divided by bracket 5 times 10 negative 8 this way and bracket. Answer is on the right side here, 2 times 10 to the negative 7. I'll write that here, 2 times 10 to the negative 7. Let me go back to this. 2 times 10 to the negative 7. Okay? So these problems are not that hard. Just remember KW is 1 times 10 to the negative 14, and then they'll either give you a hydroxide or a hydroxide or hydronium concentration, and then you can go through and calculate which is which. Now, a little bit more difficult than that is the pH scale. Really, you have to use that to convert it into the pH scale, I should say. It's actually the same thing. So now we're just going to learn how to use that on a pH scale. So pH scale, everybody is probably pretty familiar with. It goes from 0 to 14, and it tells you how acidic or basic something is. 7 is neutral, and as we said earlier, 7 means that the hydronium ion concentration is the same as the hydroxide ion concentration. Make sure I didn't leave you all on my iPad. Okay. So anything less than 7, so 0 to 6.99 is acidic, and then 7.01 to 14 is basic. All right. And so we have the different litmus papers that we talked about. That's a pH paper, pH meter, which just reads the concentration directly. The phenolphthalein is an indicator, and that will just turn color when it gets to a certain pH that we're looking for. Usually it's like 8. When I reach pH 8, it will change to pink for phenolphthalein. And then here's kind of an example of where some things are on the pH scale, but I want to talk about what pH is. So pH is the negative log of the hydronium or hydrogen ion concentration. Okay, so let's look at that one that we just did, right? 2 times 10 to the negative 7, and I want to figure out the pH. What pH is that? Okay. So pH is the negative log of that concentration. Let me go to my calculator, and I want y'all to kind of see how I do this. So let me start a new problem first. So let's say the negative log, and then it'll start this parentheses. You might have to start the parentheses on your own on your calculator. And then we said our answer was 2 times 10 to the negative 7. And then let me close that parentheses. Okay. So the pH of that would be 6.69, roughly about 6.70 pH. So slightly acidic. All right. So I just wanted to show y'all how to use log. Anytime you see P something, all that it means is a mathematical indicator saying negative log. Okay, so negative log 2 to 10, negative log times 2 times 10 to the negative 7 is 6.69, pH 6.70 or so. Okay, and then there's one other example. Yeah, don't forget about sig figs. If you're going the other way, right? If it says, let's see, where's a good question that kind of indicates that? So if you're solving for the pH, you can just follow through like that. I'll tell you what I'll do. I'll find like the problem that I'm thinking of is kind of trickier, but I also noticed on Master in Chemistry that Chapter 7, you'll have to excuse my phone, Chapter 7 on Master in Chemistry, there's a couple problems that people have trouble with, but it was expected because those are really hard problems. So there's another couple problems that you may see that's more difficult concerning pH and KW. I'll put them on Master in Chemistry, see how well y'all do, but I didn't count the ones that everybody had trouble with against you on Chapter 7. And I'll probably do the same for these. So I put harder problems on there, but it's because I want to kind of push y'all and get y'all thinking about things more in depth and also more conclusively, right? I noticed that problem on chapter 7 had a lot of different elements from different chapters that you had to kind of be familiar with and use. And so the same thing is true with pH, right? You have to be familiar with ions and balancing equations and calculating concentration and using a calculator, getting back and forth from concentration to pH or whatever. So a lot of different elements here. I'm going to include some more stuff on mastering chemistry, and then I'll also do some of these harder problems on the review when we get ready to start reviewing for the final, because that'll be coming up pretty soon. Okay. Oh yeah, if they give you the pH and you want to calculate the hydronium concentration, this is how you would do that. It'd be 10 to the negative and then enter the pH right there. So 10 raised to, for example, that one we just did, negative 6.69. So let me do that on my calculator just so y'all kind of see that. So 10 raised to the power of negative 6.69897. Okay, you see 2 times 10 to the negative 7. So if you want to go back and forth between, if they give you the pH, it's pretty much just 10 to the negative pH, and that'll give you, that's the inverse log of for pH. How to use inverse log to get pH. All right. So I think that's. Oh no, do need to mention something else. Okay, so the last thing I want to talk about is reactions are, they're here, and I'll include those. But if you just want to make like little charts, because I don't technically remember these things, most of the time it just makes a salt and a gas. So it'll be carbon dioxide. Water can be emitted as steam, and then you also have carbon dioxide, right? If it combines with any kind of carbonate. So I'm not as worried about the reactions. They may be on mastering chemistry, probably not be on the final though. Um, but it would be good practice to make sure that you can balance these equations and move things around, solve these problems. Like I said, it's not that hard. They tell you exactly what the products are going to be. Most of the time, carbon dioxide and water. And then I think the other one was, what did it say? Hydrogen and a salt. Okay, so they, like I said, they'll tell you what the reactants will be, what the products will be, and then you just kind of figure out whether or not it's being combined with a carbonate. Both of these are carbonates, so both of these will make carbon dioxide. And we talked about acid and base neutralization, right? H plus OH minus makes water. So that's all, that pretty much handles all the reactions. Excuse me. Got something caught in my throat. So this PowerPoint does have a lot of good practice on there. So go through, make sure you can do all this, and you feel comfortable with all these problems. Okay, so the last thing I want to kind of quickly touch on is buffers. Okay, so a buffer, I usually think about the blood. The blood is a tremendous buffer. It has a high concentration of carbonic acids that can both accept hydrogen protons and give them up. And so it doesn't matter if you get a bunch of acid dumped into your bloodstream, it'll start to buffer that out. It'll raise the pH of your, lower the pH of your blood just a little bit, but it's constantly pulling up those hydrogen protons to try to absorb the damage done, so to speak. And the way a buffer works is I just have a bunch Let me see if there's an equation here I can reference. Here's a good one. Acetic acid. All right, so I have a bunch of this acetic acid, which is essentially a weak acid base combo, right? So the weak acid doesn't easily give up that H, we said, right? But it does give it up, especially if there's a strong base around, right? If there's a strong base around, it'll yank that hydrogen proton right off of the acetic acid. Um, and then conversely, if there's enough protons around, then this conjugate base that's floating around in water or the buffer, whatever, will snatch up that hydrogen proton pretty quickly. And so, in this way, a buffer kind of mitigates whatever acid or base is added to a system. Okay, you have a bunch of these competing ions, and so when I add, whether it's an acid or a base, they just outcompete that acid or base. Okay, so there is, let me see. This is a good indicator right here. So the pH is 7, right? This little tool here. Oh no, I gotta back up some. I hate I did that. So I didn't really talk about anything. I just went through these reactions. Oh man, what an idiot. Yeah, so for those of you on the video, I hope you can kind of have your slides there somewhere with you, but I just messed that up. So for the reactions, like I said, I'm not that concerned with you knowing how to do this, but if you want to kind of keep a note or a note card where it says, metal with an acid creates a salt and a hydrogen gas. Metal with acid with a carbonate creates carbon dioxide and water and a salt. Okay. And then neutralization is acid plus base, H plus OH equals water. And then also make a salt. All right, sorry about that. I don't do that too often, but it does happen. This was the illustration I was trying to show y'all when I was talking about the buffer. So this is a pH meter and it's reading the water. So when I add acid into water, you see how the pH goes from 7 to 4, drops a lot, right? And when I add a base, the OH minus, it goes from 7 to 10.5 pretty quickly. But in a buffer, these competing ions, and this, I didn't show y'all this, where was that? We were talking about acetic acid, right? H2C3H3O2. These competing ions will kind of soak up whatever acid I add or soak up whatever base I have. All right, and so when I add acid to something to a buffer, the pH goes from 7 to 6.9 instead of 7 to 4 like it did in water. Add OH or a base to a buffer and it only goes to 7.1 as opposed to going to 10.5 like it did in the water. So that's the purpose of a buffer. A good buffer I always think of as the blood. It balances the pH at around 7.4, so slightly basic. And that's because you have a lot of acids getting dumped into your bloodstream at a lot of points, so it helps to mitigate those damages, right? And a lot of the enzymes and stuff function at a high pH, at a slightly basic pH. And so that's why the blood kind of buffers everything and keeps it at that constant pH for different activities. All right. So yeah, go through there and make sure you got do the little study checks. Like I enjoy doing those. Just kind of checks and make sure that I know what I'm talking about. The little chart, make sure you have your little chart or your little cheat sheet, study guide, whatever. I'm going to print one for the final, obviously, but it's good to kind of keep up with these as you go along. Your little note cards where you might have the reaction, neutralization, H plus OH minus yields water, and a salt if you're doing hydrochloric acid and sodium hydroxide or something like that. Okay, yeah, I think that's it for today. So y'all let me know what questions you have, where you're at, um, and then any bigger general questions about coming up on the final or whatever, grades, whatnot. So Anyway, that's it. For those of you in my lab, I will post that first thing Friday morning. We're doing, I think, lab 10 this week. So I'll see y'all then. Bye.